Okay, so for big O notation, big theta notation, big omega notation, you just basically you have this criteria at the beginning that says f and g have to be real valued functions, so they can't be complex. And on the same set of non-negative integers, which is normally 1 off to infinity, with g of n being greater than or equal to 0 for every integer n, greater than or equal to r for where r is some positive real number. So this is just a condition saying that eventually g of n has to be greater than or equal to 0. Okay? And so if g of n is going to be greater than or equal to 0 for some positive, for all n greater than some positive real r. Okay, so we just want that function to be continuous. To be positive at some point, which mainly means that if you're talking about a polynomial or something like that, then it has to have a positive leading coefficient. Okay, and that's going to be one of the conditions for our the order of polynomials. Okay, so this is just the condition that we're going to begin with. Okay, we just need to have a positive function eventually. Okay, but I didn't say anything about f. Okay, so what are we going to do with f? F is going to be a relationship with g of n. Okay, so we have f and g, which are positive real functions. Okay, we can say f of n is omega g of n. Okay, another way to phrase this is f of n is big omega of g of n. Okay. So we have this f and this g, and we're going to say the relationship between f of n and g of n. We already stated from the conditions, and those conditions that we stated at the beginning will apply to all three of these properties. Okay? And so we say f of n is omega of g of n if and only if, okay, there exists a positive real number, positive real numbers, this condition is a little silly, but I'm sorry. And A greater than or equal to R such that A times G of n is going to be less than or equal to F of n for every integer and that's going to be n, which is going to be greater than or equal to A. Okay, so why do we need these two integers? So in the previous statement, we said that there exists an R such that g of n is always going to be greater than or equal to 0 after R. Okay, so we know that g of n is going to be positive after R. This statement is saying, well, there exists an A past R such that f of n is going to be greater than or equal to some constant multiplied by g of n. Okay? And this is going to be true for any integer n, which is going to be greater than or equal to a. So first we have to have the r saying that, okay, g of n is always going to be greater than or equal to 0 past this r. So it's always going to be positive past this point, okay? And then we say, well, f of n is going to be big omega of g of n if f of n is going to be greater than or equal to a constant multiplied by g of n for any n past another point a, which would be bigger than r. So first r defines the fact that g of n has to be positive past this point. And then for f of n to be big omega of g of n, there has to exist another point a past r such that f of n is going to be bigger than or equal to a constant multiplied by g of n. Okay? All right, so that's big omega. All right, so we got 3 of these. Okay, now f of n, he says O of g of n f of n is big O of g of n. Okay, so we did big omega. Now we're going to do big O. In case you're curious, is there a little o? Yes. Okay. Now, when is this true? Okay, so f of n is going to be big O of g of n if and only if there exists positive real numbers okay, capital B and little b greater than or equal to r. Okay, so just like on the previous problem, such that 0 is going to be less than or equal to f of n, which is going to be less than or equal to b times g of n for every integer n, which is going to be greater than or equal to b. Okay. So f of n is omega, big omega of g of n if f of n is bounded below by a constant multiplied by g of n for every n past a certain point, okay? And now big O, f of n is big O of g of n if, well, there exists a positive real number such that, well, first of all, it has to be bigger than that r. What was that r? That was it saying whenever g of n is going to be positive. This statement wouldn't even make any sense if it was, if g of n would be negative at that point, because you actually have this inequality right here that f of n has to be bigger or equal to 0. Okay. So, big omega of f of n is big omega if it's bounded below. Okay. F of n is big O if it's bounded from above. Okay. And then we have the combination of these two statements. So, big omega is going to be less than, big O is going to be greater than, okay. Now, f of n is theta of n, and whenever, g of n, so another way to say this is, yes, f of n is big theta keep some emojis. Okay. And the theta symbol that they use in y'all's book is it looks a little bit different from that, but I'm not very good at writing that one. So I write theta like that. So f of n is big theta of g of n, if and only if there exist positive real numbers A, B, and K such that A times G of n is going to be less than or equal to f of n, which is going to be less than or equal to B times G of n for all integers in greater